Go. Hello, everyone, and welcome to the 53rd Surface Ventures keynote webinar. It'd be great to hear from you all in the chat box. So please go ahead and say hello. Tell us where you're joining from today. Great to see so many have joined already. My name is Dr. Sam McMaster. I'm the content manager here at Surface Ventures, and we are a non-for-profit organization, and our mission is to provide world-class surface and material science education for academia and industry. So today it is my great pleasure to introduce Dr. Ana Igual Munoz of EPFL. She's a senior scientist at EPFL with a specialization in tribal corrosion, with extensive experience in the electrochemical characterization, surface analysis, and degradation mechanisms of materials in corrosive environments. Her scientific interests are mainly focused on the understanding of interactions, both chemical and mechanical, between materials and contacting surfaces within the environment, mainly in the fields of corrosion, tribology, and new functional coatings. Many thanks to today's partner, Artec Instruments. Philippe Kump of Artec Instruments will be speaking later in the event, but I'd like to take a moment now to ask both of our speakers to come on stage to say hello. We'll be releasing poll questions and handouts from Artec Instruments throughout the event. Welcome on stage, Anna, and welcome.
Hello.
Great to have you. We are planning for around 60 minutes in total today. We'll be sharing a link for your attendance certificates later in the event. This will be at the beginning of the Q&A session, so please have a watch out for that. Once you have these certificates, it'd be great for you to post and tag us on LinkedIn after the event. So without further ado, I will stop sharing these slides, excuse me, and hand over to Anna, who will be sharing her slides. So just give us one moment whilst that's set up.
Thank you very much, Sam, for the super nice introduction. Let me share the screen.
Wonderful.
Okay.
Great. So Philippe and I will be leaving stage whilst you speak so that you're not distracted. So excuse me, Philippe, I'll just remove you from stage for now.
Yeah.
And I will go in a moment once I've verified. There we go. Excellent. I can see those slides. Thank you very much. Stage over to you.
Okay. Thank you very much again, Sam, for this nice introduction and give me the opportunity to show our work in tribological contacts within a hydrogen atmosphere. So thank you. Welcome everybody to this webinar. I'm happy to share with you our work. So basically nowadays it's quite popular. Hydrogen is expected to be the clean and renewable energy carrier for the future environmental friendly society. And then, of course, we have all the machine components or our installations that are not used to this hydrogen atmosphere. So how they are going to be behaving, which will be their tribological behavior, how will friction and wear can be affected in bearings, in seals, in all the infrastructure for transportation and generation of hydrogen. So this is somehow the motivation of this work that I'm going to present. Will be the tribological behavior of these metallic components that are not used to live together without hydrogen, how will be affected by this hydrogen environment. And then, of course, what it has been largely, I would say, studied are the different interactions between these material surfaces and hydrogen. For example, there are quite a lot of references dealing with this mechanism of physisorption of hydrogen molecules, followed by chemisorption of the dissociated atoms of hydrogen on metal surfaces, the possibility of forming metal hydrides. Those are just examples. Also, the mechanism of diffusion and where the hydrogen is trapped within the materials and their interactions with the metallurgical structure of those materials. Then, again, I come back to the questions that we want to address. How this tribological contact will influence the interactions. So which will be the response of the materials to these interactions. So At this moment, I checked a little bit before starting, of course, what was already, which were the main observations of people dealing with tribological contacts within hydrogen atmospheres. And then I was a little bit surprised because, of course, there were a little bit contradictory. In some cases, they were observations in which hydrogen had no influence or increased a little bit the friction. In some other cases, hydrogen was capable of increasing or lowering wear, depending on the microstructure, depending on the charging conditions. Then also people has tried to determine, quantify, which is the critical amount of hydrogen to start really damaging the material. And recently also our colleagues from Luleå, they were working with rolling sliding contacts, and then they observed, they had a similar approach that we have here. They observed that the surface damage follow the concentration of the hydrogen diffusing in the material. So at the end, the classical hypothesis at this dislocation blocking effect of hydrogen cannot explain all the observation. And then our question is, are also experimental factors playing a role? Because this is this is the first thing when we measure how we are measuring. So before starting testing, we were wondering, we put ourselves several questions. First of all, how we introduce hydrogen in a well-controlled manner in the material. We can use gaseous, aqueous conditions, how long it will remain in the material while after charging and during the tribological test. And then one thing is how to, in a well-controlled manner, introduce the material, but then is to quantify how much it has been intaken by the material. And then, of course, how can we discriminate the multifactorial effect in a tribological contact that we may have? How can we distinguish this effect of hydrogen from other material or surface effects? So, which is the goal of our work? Is the goal of this presentation in this is to assess the influence of these experimental conditions when we try to understand the effect of hydrogen-metal interactions. And the strategy is, we come from an electrochemical background, so okay, we use a simple electrochemical setup to charge in a well-controlled manner the material. Then we try to determine if the effect on the material is a fact. So we can measure changes in fracture energy and hardness, and then we carry out tribological tests. And then under surface conditions, well-controlled surface conditions. To do that, we do dry sliding, but we also use the triboelectrochemical setup to impose certain surface conditions, passive conditions to mimic the typical corrosion conditions, for example, for steel, and cathodic conditions to keep the hydrogen inside the material to avoid that it goes through during the tribological testing. And then the second part also, one thing is this ex situ charging, but then we went one step further and then we try to do the same, but with an in situ charging that I will explain later, that was done in collaboration with ERTEC. So just before starting, just few words about the mechanism through which electrochemical charging of hydrogen into metals takes place. So basically it takes place because of the reduction of a water molecule when we are in neutral or basic medium, and through the proton reduction in an acidic medium. So here by a cathodic polarization, so we force the reduction of the proton into the hydrogen. This hydrogen, this hydrogen is absorbed first of all in a first step into the surface, and then what does? It can do this hydrogen absorbed on the surface has two options: either entering into the metal, either meeting another atom absorbed on the surface and forming a hydrogen bubble. So this is the two possibilities. Then this depends what this hydrogen adsorbed on the surface, what will do will depend on several factors, surface factors, electrolyte, and also polarization conditions. What we did is a very simple charging. So what we use is a solution which is this sodium sulfide, because there are certain species like the sulfides that inhibit the recombination of the hydrogen. So with this solution, we are favoring the hydrogen intake into the material. And then we'll just apply a certain current in between an inert anode. Typically, we took this dimensional stable anode. Typically, is titanium covered, but some coatings. And then the cathode is the material we want to charge in hydrogen. In this case, was a steel. Then we apply a certain current for 24 hours. And in the first case, what we charged was a Charpy sample to try to identify which are the consequences of the charging on the properties of the materials. So the first questions, as I was saying before, has hydrogen penetrated the steel? If we look at the harness didn't change at all before and after charging. However, the amount of absorbed energy of this steel during fracture was decreased around 50% after discharging of 24 hours. Even more. This effect of the hydrogen was remain the same over several hours. We can say this is the fracture energy also after charging 24 hours and leaving it open air for 3 hours. So the decrease in fracture energy didn't change during this period of time. That was one good news, because we have a little bit of time to carry out the tribological test, and the effect of hydrogen is still there. On the other hand, the difference in between the charging effect when we charge 24 hours or 48 hours was not really, was nothing, was exactly the same. So with this test, we already know that the hydrogen, we have the hydrogen intake, so we can define some tribological testing conditions. We did it in a Taylor tribometer, a homemade ball-on disc tribometer, under different environmental conditions. So we repeat the same exercise, charging 24 hours the steel. We are going to wrap against an alumina ball, 6 millimeter diameter, to impose a certain contact pressure with a sliding velocity of 20 millimeters per second, stroke length 4 millimeters for a certain number of cycles. And then what we change are the surface conditions. We did test dry, but we did it tribocorrosion test under well-imposed potential electrochemical conditions, which means cathodic potential. This implies that the hydrogen remains within the material, and then in presence of surface field. We do that applying an anodic or passive potential. So this is the sequence, the experimental sequence we did, and this is the experimental setup. Basically, we have a linear motor that moves back and forth and transmit a weight that transmit the load into the sample. We measure the normal load and the frictional load through a 3-axial force transducer, and all inside an electrochemical setup with a reference electrode that allows to impose this surface condition, the potential, and a counter electrode that allows for the measuring of the current, which is directly proportional to the reaction rate. And then we impose these conditions, and we wrap, as I said, through this moving arm up and down. What are the results? What we measure? First of all, under cathodic potentials, as I said, here the hydrogen remains inside. So at the beginning, when we impose the electrochemical conditions, we just measure the current in the sample, is negative, because we are again reducing the water. And when we start rubbing, the current went down a little bit. This is small variation in the current can be attributed to the increase in the mass transport of oxygen towards the surface, also because of the pin motion, also because of the roughening of the surface. But we have this decrease. In the non-charge transfer, we see slightly different behavior of the current, of course, because we are somehow reducing the water on the surface, and we didn't observe any main difference in the coefficient of friction. Then we go to see what happens on the surface, and this is the optical image of the non-charged and charged samples. And we see in the non-charged this kind of nice plastic deformation with this smear and uniform wear track. The width of the wear track is more or less the same, and in the charged sample, it seems that we are blocking the plastic deformation, like we were generated at more disrupted surfaces. So we see already differences. We could go we went a little bit further in the analysis. So now we cut cross section, and we perpendicular to the sliding direction. So this is the wear track. We do a FIB cross section, and then we can see not only the surface, but also the subsurface, what happened inside the material. And what we observe is this kind of formation of blisters on the non-charged transfer, so with even local delamination of this very smeared material. And in the charged sample, the hydrogen uptake blocks somehow the deformation, and then what it generates is more accumulation of strain, so a little bit of embrittlement of the material, grain refinement, little bit higher grain refinement compared to the non-charged sample. So we see differences even if we have the same shear. Then we go to the other situation. Now we apply a passive film. So we form in a well-controlled way a surface film on top of it. And here the protocol is always the same. We impose the electrochemical conditions and we register the current. So we already see from the non-charged red curve with respect to the blue, we see a difference already from the beginning. The non-charged sample shows a very low current at the beginning. Of course, at the onset of rubbing, the current increase because we are mechanically detaching this oxide layer and accelerating the corrosion of the underlying metal. So current increases. In the charged sample, in this case, we have when imposing the electrochemical conditions, an abrupt, huge increase in current, and then an exponential recovering. So this is typically we are oxidizing something. What we are oxidizing, we will see in a moment. The coefficient of friction, more or less, is very similar in both cases. We do the same. We have a look to the surfaces. In both cases, also they are very similar. The wear morphology, plastic deformation, and presence of third body, and the same width of the wear track. And if we do again the cross section, this is the sliding direction. Here also at the subsurface level, we see more or less the same features. We see this third body. We see this smear material. We see cracks. Subsurface cracks, surface cracks. So basically, we see more or less the same effect, same grain sizes. So what has happened? Our question is, are we sure we have inside the hydrogen we have taken during the charging? And then to verify that, we did just again an extra test just imposing, when passivating when we want to passivate the steel, of course, we have to apply an anodic potential, a certain potential. And what happens is that we register the current at this potential. Here there is no rubbing. In the non-charged and the charged sample, we see a difference in current, means a difference in charge during this period. What happens is all the hydrogen we have at the surface and inside the material, because of the oxidizing conditions, we are oxidizing it and is leaving the metal. So at the end, the response of the material charged and dissolved in hydrogen is the same that the one that is only passive. So the difference in current corresponds to the oxidized in between the non-charged and charged, corresponds to the oxidized hydrogen. And then we can easily calculate this amount of hydrogen that corresponds, assuming a certain diffusion coefficient, the maximum amount of hydrogen that we can put inside the material. So the adsorbed hydrogen can be easily removed under oxidizing condition. And that means that this embrittlement that we observed during passive conditions, it was not due to the effect of the hydrogen, but mainly to the fact that you have a presence of a surface film, a passive film on top of that. This is already known in tribocorrosion. It's called the Roscoe effect. So the main effect of this passive film is that they generate and block the dislocation. So we start accumulating here a lot of strain. We cannot eliminate the dislocation because we have this passive film. So the effect is an embrittlement effect. Whenever we don't have surface films, this dislocation can be annihilated on the surface, and the strain accumulation is a little bit limited. So this is the explanation why we have the same response in the case of charged and non-charged samples. And then, and also, this can help us to also explain and to understand why under dry conditions, what happens. The steel has an air-formed, spontaneously air-formed oxide film. And what we observe is, again, it's very similar friction, but in the non-charged transfer, we see this smear third body on the surface that is broken after certain degree of strain deformation. And in this case, we see a little bit more brittle and cracked surface this is the charged sample, and this is the non-charged transfer sample. On the subsurface, the differences are even more clear. In both cases, the mechanisms are more or less the same. We have the third body here in the non-charge. We have the third body in the charge. We have also the subsurface deformation, the tribological transform part of the subsurface. Here is a little bit thicker. But in the charge sample, we have a thicker third body. We have a cracked surface, and then we have a higher degree of recrystallization of the formation. The grain size are slightly smaller. So there are differences. In this case here, we are not taking out the hydrogen by the electrochemical imposition of the oxidizing condition. So it's still there. What happens when we charge, when we load mechanically, this is another question. As a summary, I can say that here we have quantified the grain size here, the grain size of the material as a function of the depth, how depth we measure this grain size, being 0, the surface. And we see here that the main differences, they occur in the cathodic conditions, whenever we keep the hydrogen inside the material. So the charged sample, whenever we have this hydrogen, we decrease the grain size overall the studied subsurface depth. In the case of the passive charge or no charge, there is no difference. And in dry, we still at the very surface, we see a small difference. Finally, these observations, what they demonstrate is that hydrogen effect is strongly dependent on the electrochemical conditions in the presence or absence of surface films, even though we may have the same wear mechanism. So, from this point of view, this work allowed us to, first of all, conclude that the electrochemical charging is effective, and we can quantify through measurements, simple measurements as fracture energy. And then this influence of hydrogen is really influenced by the testing conditions. Either when we don't have these surface films, we work under cathodic condition, hydrogen is confined in the material, and then we see the difference in plastic response of the steel. Under passive conditions, we don't see it. There are other effects that play a role. And under dry conditions, again, there are a combination of the fact that we have surface films and we have also still the presence of hydrogen. So this is all these effects, again, still can be explained with this dislocation blocking effect of hydrogen, but take care about the presence of this surface films. So now we do the second iteration, the reflection from this work. We say, okay, whenever we design experiment to assess the influence of hydrogen atmosphere in my material, in my machine component, we have to ensure this effective charging. We have to ensure that hydrogen is not lost during the experiment, and we have to be sure which other factors that causes embrittlements are considered. So for that, we went from an ex situ experiment where we charge and then we do the tribological test to an in situ conception of the testing conditions. So this is basically is based. So we developed together with ERTEC an electrochemical permeation cell. Based on the classical permeation technique that was introduced by Devanathan Storsky. This is known in electrochemistry, where we have a thin membrane, in this case is our steel sample of 3.5 millimeters in diameter, and then we charge under the same conditions we observed in the previous example. We charge in the entry chamber the steel, and it flows, it diffuses through the sample, where on the exit chamber can be quantified or can be oxidized and wrapped. So in the generation chamber, we reduce the proton. In the exit chamber, we can oxidize the proton, so quantify the hydrogen flow. So this is typically an example of how the quantification of this flow. We impose certain conditions in the exit chamber. So we register the current. At the beginning, we passivate, and then we start charging the bottom part. Just from the current and using the Fick's law, we can extract directly the diffusion coefficient of hydrogen in my specific steel. So this current is directly proportional to the hydrogen flow I'm going to have in my system. This system can be a little bit more elaborated to determine exactly how much hydrogen is trapped in the steel, because and then we do just a mass balance. I know the amount of energy I use, the amount of current I use to reduce the proton. This proton will be part enter into the steel, part will be recombined, forming hydrogen. If I have a hydrogen sensor in the solution, and I know the amount of hydrogen that has been recombined, I can determine how much has gone through. In the exit part, I determine this diffused hydrogen. The difference is what it remains on the steel. This is another way to determine the amount of trapped steel in the trapped hydrogen in the steel. So this is with respect to the generation of the hydrogen flow, and then the quantification of this flow. But then we can the permeation cell, we can place it into inside a tribometer, and this is what we did with ERTEC. And then basically we can, for example, put here our permeation cell, have a look to the current which is proportional to the hydrogen load. We apply the load, and when applying the load, because of the stress distribution within the material, we change the flow rate of the steel. This is one just by static loading. We don't wrap. So the static loading, the generation of this stress field, influences the full flow of hydrogen at the exit. And now we wrap. We can wrap against an alumina ball, the same conditions as we did with the ex-situ experiments, the same sliding velocity, the same normal force. And what we see, if we compare the coefficient of friction, we start seeing some differences in between the ex-situ, the tribological response in the ex-situ cell compared to the tribological or coefficient of friction in the in-situ cell. This is under dry conditions. Have certain scattered and slightly different coefficient of friction. What we observe then is when we have a look to the surface, the non-charge, the charge wear, the wear track of the charge transfer charge sample ex situ, and the wear track of the charge. Sorry, this is charge ex situ, and this is charge in situ. We see that we have different wear depending on these charging conditions. In this case, we have thicker and higher cracked surface in the charging condition. This is an ongoing work, of course. We are now trying to understand this interaction, hydrogen and material, but still developing the smarter way of carrying out this test to answer the question of the interaction hydrogen-metal under tribological conditions. So, with all of this, I would like to conclude this webinar by saying that this, if we want to understand the interaction of materials and hydrogen under tribological conditions, we have to think very, very carefully how we want to carry out the experiments, and then to take care of the already developed concepts in tribology and then in tribocorrosion, because here now we are in a reactive environment. Hydrogen is a reactive environment, so really we have to think twice, and for that we have concepts. Then there are different things. One thing is that we operate on the continuous flow of hydrogen. This is the in situ measurements. And another thing is that we just charge and then we test. The questions to be answered, it will be different, and this also will depend how we test the operating conditions of the machine component we are addressing. So in any case, the hydrogen flow effect can be assessed with these tailored experiments and specific permeation cell coupled to a tribometer. And then, of course, then we can start answering the real questions about the effect of stress-induced deformation on hydrogen intake and uptake. And this, again, it requires to be aware that during testing we are generating, we will have, depending on the testing condition, a certain surface with a certain properties that can modify the outcome of the hydrogen-metal interactions. I would like to thank a lot all this of course is something that I did not alone. I work with all my colleagues from the EPFL. We work in very close collaboration with the ERTEC people and also with the University of Technology of Warsaw that was also involved in the Exitu study. With all of this, thank you very much for all your attention. And now any questions, I will be super happy to answer. Thank you.
Thank you very much, Anna. So we'll switch to Philippe's talk now, and then we'll take questions afterwards. Thank you very much. So sorry, Philippe, once you're coming on stage, let me just get your
yes. Good morning.
Good morning. There we go. There we go. Slides are up. Stage is over to you. Please go.
Yeah, thank you, Sam, very much, and thank you, Anna, for the very nice presentation. So, giving the talk that was on hydrogen tribology, I will try to give a few insights about the testing capability of Arctic instrument combined with hydrogen and tribocorrosion, which are related subject to the talk of today. And the very nice presentation from Anna. So before I go into the detail of this particular testing method, I just would like to remind a few people or to inform people that are not aware about the activity of Arctic Instrument. The headquarters of the company are in USA, but there are in fact offices in different parts of the world between Europe and Asia. And Arctic Instrument develop and manufacture advanced mechanical surface testing equipment for different research application and industrial application. The idea in general is to give a very good insight about combination of mechanical property and tribology property of different material. And when you go into mechanical testing and tribology testing, it is true that it covers a lot of range of different application. Arctic Instrument has been very famous with a multifunction tribometer that imply a different model from the MFT 5000 to the MFT 2000 tribometer, from tabletop instrument to more advanced equipment in the laboratory for different testing of friction and wear of material. But when you cover a lot of environmental condition of testing, you might be interested in vacuum testing, in high pressure testing, and therefore we have different model of different environmental control equipment that are able to do testing in different environments. Of course, in the field of tribology, you have also different testing method, and fretting test is in reality a very specific mode of testing where you can study high frequency of oscillation for low amplitude, and that requires specific designs that are provided by the fretting tester. Arctic Instrument have been involved quite a lot about mechanical testing as well, where we have a surface material tester that covers scratch testing and nano and micro indentation testing for the field of mechanical property characterization. And for the different other application in tribology, it also covers lubricant testing, where you could have different kind of equipment with a different sliding rolling ratio in order to have not only testing with sliding condition, but having different condition of testing where you can change the condition between rolling and sliding for lubricant characterization, or even certain application about material characterization. So therefore, you have a twin roller where you have two cylinders in rotation, micro pitting tester or three roller where you have a three roller in contact with the sample, and universal traction machine or mini traction machine that allows to characterize traction curve and strike curve in tribology. Arctic Instrument has been quite famous for combining 3D profilometer with tribology, and it is true that it also proposed a standalone unit. And in the field of erosion testing, you have the characterization of erosion tests that is also a specific field of tribology that has been that has gained, in fact, a lot of requests this year with the application about aerospace and turbine. There is a presentation or a slide that I don't have present here, is that because Arctic Instrument has been involved quite a lot about micro-mechanical testing with scratch and indentation at room temperature, there has been a strategic partnership and a new information about the collaboration and strategic partnership between Arctic Instrument and Macromaterial. And there is a new press release that has been done last Monday that I would invite all the people to look for new information about the extension of capability of measurements of nano and micro indentation at high temperature, for example, that will give even more insight about an extension of the range of application that we have for the application of mechanical characterization. So to a little bit continue about really the application of today is that in the recent years, there has been a lot of requests about electrified tribology, being able for a fluid or grease to characterize the combination of lubricant characterization with electrification. And it's true that has been requested quite a lot for tribology testing. So either you go with a 4-ball test, linear oscillation, mini traction, fretting test, or high frequency oscillation. There has been quite a large demand of electrification. The interest behind that is that there are a lot of need of the industry of doing testing in tribology with electrification. Of course, it comes from the electrical vehicle, hybrid vehicle, where you would like to test a gearbox, e-motor, where there might be stray current remaining, and that influence, in fact, the capability of wear resistance of different material and the combination of lubricant with material in presence of stray current might influence the wear resistance of the material. Therefore, having options like electrical contact resistance combined with the possibility of tribology testing with load and speed gives you a good insight about laboratory testing in different kind of conditions. So either it could be electrical contact resistance measurements, potentiostat, which is applied with DC and AC current, but there are, in fact, a lot of different application and conditions that could be related to that. But it is true that the collaboration that was done with EPFL has the advantage to generate or be able to propose a hydrogen cells that I will show you later. But the big advantage, it has been also possible to develop a tribocorrosion cell of a new generation based on these hydrogen cells that was gained as a better understanding of what are the best condition of testing for that. So the tribocorrosion cell, if you are not familiar, has the possibility with a 3-electrode system to have the sample, which is as a working electrode, then having a reference electrode and a counter electrode of generally platinum in order to have a 3-electrode system being able to apply a potential and then measuring the current on the setup. So that's in fact represent very nice application where you could simply apply a potential. So you can measure initially the open circuit potential where you see the current under the open circuit potential condition. But by applying a potential, then you can create a passivation or depassivation of the material and simply see the evolution of the current without or before starting a tribological test. But of course, after, if you start a tribological test, you are able to measure the corrosion kinetics and then having a useful information of either what could be the wear and coefficient of friction of the material under applied potential, as well as measuring a current of the corrosion kinetics with this kind of setup. So that's kind of a setup which is possible on a linear turbometer and is a nice add-on for different tribocorrosion studies for materials. But what is even more or an advantage for testing is this combination for hydrogen tribology. And it's true that there are a lot of requests about testing for hydrogen in the recent year. And I will just spend a few minutes to explain you a little bit what was the request on the market, because for many years, people are interested to do tribology under hydrogen environment and hydrogen condition. And it's true that there have been a lot of requests for high pressure turbometer. But high pressure require a certain condition of testing with a specific chamber. The interest for hydrogen tribology has been up to high pressure of 100 bar. And of course, high pressure hydrogen requires very strict condition of safety and regulation, meaning that for a lot of cases, the budget of an equipment is much lower than in fact the budget that would be required to build a specific laboratory, meaning that the hydrogen turbometer is an equipment that would not be possible in all kind of laboratory, because it requires really a specific laboratory to be able to accept an equipment. And the idea behind the development at EPFL is really to have the possibility of doing testing with a hydrogen charging of material. The big advantage is that the cell is small, so it's compatible to standard laboratory condition. It is possible to install it on an existing turbometer and to make easier simulation of hydrogen phenomena, meaning that you can create hydrogen embrittlement in material on a relatively more simple setup and be able to do already advanced study on hydrogen embrittlement with a turbometer. Of course, these kind of two ideas are complementary. It does not mean that we'll replace whole hydrogen turbometer, but it has a big advantage to be able to do on in a standard laboratory without strong safety regulation, the testing under hydrogen. For those of you that are not familiar with electrochemistry, the idea behind is relatively simple, is that if you apply a potential under a liquid environment, you are in fact able to generate hydrogen. And this simple idea in electrochemistry was taken as an advantage in the setup in EPFL in order to generate hydrogen simply by applying a potential in a specific liquid solution and be able to generate hydrogen and simulate hydrogen embrittlement in steel material as an example. Of course, there are many technical details on this hydrogen testing, but it is in reality a relatively easy add-on to an existing linear turbometer in order to do study under hydrogen embrittlement, hydrogen environment, sorry. So the idea behind is that for this kind of hydrogen studies is that you're going to have still the application where you can charge the material under hydrogen at high pressure, then try to do in situ measurements under high pressure. But the idea behind here is really to have a setup of electrochemical charging and to be able at the same time or just after to do tribological tests. And this cell is relatively small in size and has really the advantage to be able to be added, to be installed on a standard turbometer and to do already advanced studies. So I'll show you a little bit the application and the application of hydrogen on existing turbometer. I did not give you in reality all detail, but we would be happy with EPFL and Artec instrument to give you really more technical detail about this setup if you are interested in this range of application. So I will give back the the word to Sam for finishing this webinar. Thank you very much.
Thank you very much, Philippe. Also like to invite Anna back on stage, please, and we'll take questions in a moment. Whilst Anna's coming back, let me just release the attendance certificate link, so that is there for you all now. But please don't go. We've got a number of questions that we'd like to go through. Quite a few good ones. So here we go. So our first one is from Oshwan. I hope I'm pronouncing that correctly. Apologies if not. And they ask, could you please explain the procedure between the charging process and the subsequent tribological testing? How are the samples handled and stored after charging? What is the allowable time interval between charging and testing? And how critical is this timing? So I think that's for you, Anna.
Yeah, I think I can answer. Yes, basically is what I try to show with the Sharpie test. Basically, what we did, we charged for 24 hours. Then it was just rinse, clean, and not a storage. Directly went to the tribometer to test it. We did this, so, and then is what I'm saying. We after 3 hours of the charging, still the effect in the fracture energy still is there, so we don't lose it. After, I think it was 12, 24 hours, just if you leave the samples like it, we recover the fracture energy of the initial steel. So really the more or less. So really the hydrogen trapped in the steel was really gone. So we had this desorption, and in fracture energy we didn't see any effect. So if you want to charge XC2, yeah, I guess you have to charge and afterwards directly try to test your material in your tribometer, basically.
Okay, thank you very much, Anna. We've got question from Mohammed, and I think Philippe, this one's for you. Mohammed says, we have an Arctic Universal Tribometer MFT 5000. How can this be used for tribological testing under electric or hydrogen charging?
So there are two options. One are electrical, and then the other is hydrogen charging. In fact, the hydrogen charging cell is really a new option that we have from now on, basically from the month of March. So if you have a linear, the possibility to do linear oscillation, you would have to acquire this hydrogen cell charging cell and install it. It's not a setup rotative, it's linear, but it could be the linear module or the motorized stage to do the oscillation. So it's simply an add-on to the instrument. Electrical measurements are available on different modules, rotative, linear, and so on. It requires for certain setup, like a 4-wire setup, to be electrically compatible, meaning that we have to isolate the sample from the rest of the instrument. For a linear setup, it's really straightforward. For rotative, we have to make an upgrade on the instrument, but that's basically add-on to the existing instrument.
Okay, brilliant. Thanks, Philippe. I got a question from Mustafa here, who asks, I think this is in reference to Anna's work, but Philippe, please do also, add anything you feel. How sensitive is the electrochemical cell? And also, does this sensitivity change in combination with the tribometer? I presume that's what they mean.
What do you mean by sensitive?
I imagine it meaning resolution in terms of, although that would be more down to the...
Okay, here, I mean, if this, the electrochemical, there are two things. In the in situ, what Philippe was saying, for charging, we just need a small power supply to provide the electromotive force to reduce the water into hydrogen. This is you don't require very sensitive. Then in the upper part, if you want to really quantify the hydrogen flow through this permeation cell, then there you need typically you need a potentiostat, what a 3 electrode setup, and then there is I mean, you can the current is directly proportional of the amount of moles. I mean, the number of atoms of hydrogen you are extracting. So it's really you quantify the atoms from this point of view. Yeah.
Yeah, if I can add on just a comment,
Yes.
it's true, like in tribology, there is certain aspect to be careful when you do testing, especially cleaning. So it's very known you have to clean the sample very well, because any lubricant or contamination on the material can have an effect. And it's true that electrochemistry has also its own small detail to be very careful when you do testing, I think. You could have contamination of the contact electrode. You have a little bit to be careful about the sample preparation. And that might be maybe the question, is that you have a little bit to be careful how you prepare the sample. The same way in tribology, that you have to be very careful to clean the sample. But on the setup is on the machine, then you can start the measurements relatively easily.
Okay, thank you very much, both. Further question from Mustafa. I think this is one specifically for Anna. Just to ask, which method in the potentiostat is used for the hydrogen charging?
Yeah, I mean, it's what I said. In the entry part, it's just galvanostatic. We imposed a certain current density, and that's it, which is proportional to what the amount of water proton you are reduced. In the exit part, we use a potentiostatic method. So in this case, the solution was a basic solution, sodium hydroxide, that allowed for the passivation of the steel, and then we imposed a potential that passivates, and when it's charging, it above the passivation. So passivation means that the current will go very, very, very low, and when you start charging, you will see the current increase because of the hydrogen oxidation. So you have to, depending on your material, but basically the permeation cells, they use potentiostatic methods at a potential that can vary a little bit depending on the type of steel you are using.
Okay, fantastic. Thank you very much. The question here from Ajay, or perhaps Ajay. Apologies if I'm mispronouncing it. I think for Philippe, and Ajay is just asking, is it possible to use the Artec twin disc roller tester for rail wheel applications?
Yeah, I think today we did not present too much the twin roller. So for those that are not so familiar, it's a system where you have 2 cylinders in rotation, then you apply a load laterally, and then you measure the wear about the wear and the friction about two twin disc. In reality, one of the biggest application has been for rail wheel application. The bigger number of requests we got for this application and been on a rail wheel. For some application, it was the idea to put a solid lubricant on the cylinder, so on the simulation of the rail wheel with a solid lubricant on the surface. And first of all, the measurements of the coefficient of friction in presence of the lubricant, but also the lifetime of the lubricant. Is how long is going to be the test before the lubricant goes away and then the friction coefficient increase. But it's true that the twin disc has been quite a big request with rail wheel application. Yeah, I would recommend that to contact Artec Instrument for discussing all the technical detail of this particular instrument that was not presented today.
Okay. Thank you very much, Philippe. I just noticed we're almost at time, but we have 3, I think, relatively simple questions remaining. So if you both are okay with that, we'll spend a couple minutes answering those.
Sure.
Okay.
Yeah.
Wonderful. Question from staff of us: is there a hydrogen permeation measurement device for membranes or non-metallic substances? Philippe, I think this is one for you. Although Anna, again,
Anna may
Yes,
answer.
maybe
better,
me I
perhaps,
can.
actually,
I mean,
sorry.
the charging is based on electrochemical conditions. So to apply this electrochemical condition, we need metallic contact. But of course, all the transport of the permission measurement, the transport through non-conductive, it can be assessed as far as you can, for example, do just 1-2 nanometers PVD coating on both sides of your non-conductive material to have the connections to apply the potentials for reducing the proton and for oxidizing in the upper part, and then you will see the transport properties for hydrogen. But as a matter of fact, the surface at a certain point you need a conductive material. The transport of hydrogen through a non-conductive is feasible also with this permeation concept.
So you would need, like in that case, a 2-layer system where one layer would be the metal that needs to generate the hydrogen, and after it can go through the
you will have your
polymer, for example.
Yes, your polymer, your membrane that is not conductive, and on top and on the bottom you have to make it conductive somehow. You can deposit, I don't know, gold layer, platinum layer, whatever, on both parts, and then you can do the contact here for oxidize the proton, and in the bottom part for the reducing the water.
Brilliant, thank you very much. A question from Rohit, who asks, why are both dry and cathodic conditions tested in sequence for hydrogen-charged samples?
No. We're not, sorry, I didn't explain myself. We're not tested in sequence. We did under dry conditions and we did under cathodic conditions. Not for sure, we're not in sequence. It was, no. Probably I didn't explain myself in a proper way, so no.
No, I think it was one iteration of testing and then another iteration of testing, as opposed to...
Each condition was a full independent test. Yes.
No, thanks, Anna.
You're welcome.
Okay. One from Mohammed, I think very much for Philippe here. So what is the price of the electrochemistry and hydrogen cell that can be integrated into the MFT 5000, if you have that to hand?
We have not finalized the final price of the hydrogen cell, so we would be happy to send you a quotation. But there is the price configurator that will allow to make the price offer, but we would be happy to send you an offer. That's no problem. But today I don't have the final version.
No, that's fair. I think he's said as well that they have
But
both.
it's true that there are two versions. There is one which is a tribo-corrosion cell, which is a simplified version of the hydrogen cell, because you just have the sample, and then the hydrogen is almost like an additional setup to generate the hydrogen. So in theory, with the hydrogen cell, you could also do a simple tribo-corrosion measurement.
All right. Thank you. Yeah, just to know, I think he said that they have both rotating and linear options, but as we said, so I'll when I pass details on, you'll have the chat log, so you can check who to follow up with regards to questions like that. And then our final question today, also from Mohammed. Thank you for all the questions. He said, what is the distance between the working electrode and the reference electrode?
This is a super good question. In principle, this is an electrochemist, I guess. You should, in tribocore, you have to consider that in between the reference electrode and the working electrode, you will have an electrolyte. An electrolyte, a solution, is an ionic conductor. So you will have always resistance, and as a function of the current you have in the system, you will have an ohmic drop. So as a general rule, it has to be as close as possible to the working electrode. In this case of these horizontal cells that you are approaching is fine. The only thing is what you measure. For example, in tribocorrosion, the cell that we are, Philip is also presenting, when you wrap, of course, the wear track is far. The reference electrode is far away from the wear track. So what you are measuring is the potential outside of your wear track, because inside you will have you can have a huge ohmic drops. So just to be aware, you have to be as close as possible of the reference as of your working electrode, without touching, of course. But when you do tribocorrosion, take care, because then the information is of the outside the wear track. Inside, as far as you have certain geometry, you will have a not negligible ohmic drop. In any case, this you can quantify. They are theoretical models that, depending on the radius of your ball, the exact loading, how much you dig into your sample, you can determine this ohmic drop. So you can know exactly which is the potential within the wear track. So, as close as possible, but take care in tribocorrosion that you have a wear track, and inside you don't have access, because you can put you cannot go that close with the reference electrode.
Yeah, wonderful. Thank you very much, Anna. And I think with that we've worked through all the questions. And now to the end of our event. So thank you both very much for your
Thank you, Sam, for the nice
fantastic.
organization.
Thank you for the invitation. Yeah.
Yes.
You're both very welcome. Thank you, and thank you to Artec Instruments for the support for today's event. Thanks as well to everyone in the audience for your excellent questions and for being here throughout. As a reminder, please do visit surfaceventures.org. You can view our next event, which will be updated on the website soon, but you can see right now the link is that is there. Let me share the link for that. So if you're interested to register for our next talk in May with Professor Ben Beek at Micromaterials, please do go ahead and click that. Yes, we will be keeping you updated on LinkedIn and via emails with any further updates. And finally, I'd like to say, please do take the time to advertise what we do to friends and colleagues, anyone that might be interested. It'd be great for us to keep growing our audience and reaching more people in the worlds of tribology, surface engineering, and material science. So with that, thank you all very much, everyone, and wishing you all a very pleasant rest of your day.
Thank you very much.
Thank you very much.
Sam. Thank you,
Thank
Anna.
you. Thank you very
Bye-bye.
much.
Thanks
Bye.
very much, everyone. Bye.